Hello, class. So in this video, we're still continuing on our first session of, of the course material, which is based on chapter 1, the first few sections. And in the last video, we were talking about different types of differential equations. Basically, we have ordinary or partial differential equations. So we did examples of how to differentiate between them. And I'll just review with another quick example. So is dy dt plus dx dt minus y of t plus x of t equals 3, is this an ordinary differential equation? Okay, so think about it. Remember, ordinary means derivatives with respect to a single independent variable. Doesn't matter how many functions you have. So based on that, this would be an ordinary differential equation because even though we have more than one function, in this case we have y as a function of t and x as a function of t, we're taking derivatives only with respect to the variable t. So it's an ordinary differential equation. Okay, now what about this one? We have the second derivative of y with respect to x plus y of x equals 2 times e to the t. So is this an ordinary differential equation or a partial differential equation? Well, it turns out that even though there's two independent variables here that show up, namely there's the x and there's the t, since we're only taking derivatives with respect to one of the variables, you only see derivatives with respect to x, this is still an ordinary differential equation. Because again, you're only taking derivatives with respect to one variable. So these are both ordinary differential equations, ODEs. Now, as I mentioned, even if we have an ordinary differential equation, we usually won't be working with more than one variable. Even if the variable that we're working with, we're not taking derivatives of, right, so it'd still be an ordinary differential equation, we're usually just going to be working with one input variable or one independent variable. Now, I mentioned before that I have two different sorts of notations for functions, for derivatives. You can either use this notation, y prime of x, or this notation. Now, I'll use these notations interchangeably, and in fact, if it's clear what the independent variable is, I'll even drop the value x. So for example, I could write a differential equation like this. And if I don't write anything, so I don't write that these are functions of x, then it should be clear, even though I don't write y of x, it should be clear that y is a function of x. Y is a function of x, or y prime. Y double prime is a function of x. So any case this is clear, I might just drop the parentheses x and just write y double prime, or y prime, or just y. And again, this is a case where it's clear because I've told you we're only working with one independent variable, and you can see that the independent variable is x. So the only option is that all of these functions here are functions of x. Okay, so this is a case where I could see it's obvious that these are functions of x, even though I don't write it explicitly. Okay, just one thing to note. So if you see something like this and you don't see the parentheses x, don't freak out. That means that somehow it should be obvious what the independent variable is. Okay. Now, I've said that we can use, or that this class is kind of interesting because now we can start to use calculus to model things in the real world. And as I mentioned before, we're kind of restricted in the things we can model because we only have one independent variable, but we can still model a bunch of things. And what we're going to do here is derive a model that determines the position of an object that's falling. Right? So falling vertically, and I make here the note that it's near sea level because if you get too far away from sea level, and by too far I mean like very, very far, like close to the atmosphere, then the formula that we have for gravity, we know that gravity is given by 9.8 meters per second squared. This starts to change a little bit. So I just make here the specification. This is near sea level. But now we're going to use our knowledge of calculus first to derive a model, for this sort of situation, or for this system, is usually what you would say, a model for this system. And then we're going to use our knowledge about, okay, I want to find solutions of a differential equation by taking integrals to find solutions to the model that we come up with. Okay, so let's start. Now, notice that I talk about a falling object because, like I mentioned, we only have one dimension to work with, right? We have one input variable that means really just one dimension, 1 degree of freedom. So if you think of how an object falls vertically, that's really one-dimensional motion. Whether it's moving down or whether it's moving up, right? It moves along a single line, so that's one-dimensional. Okay? So there's no planes or stuff like that, just a line. So we're looking at one-dimensional motion. We should hopefully somehow be able to model this using our knowledge from calculus. So let's start. So let's first think about if we have a falling object. So let's say we have a rock, let me draw it like this, a rock that's falling vertically. Let's first think about what forces are acting on this rock. Okay. So one force that we can think that we know that's acting on the rock is, well, the rock has weight. Right? Of course, the rock has some weight. If you put a rock on a balance, on a weighting balance, it'll tell you, oh, it's 5 kilograms or 0.5 kilograms or 7 kilograms. That weight is actually a force. So let's call F1. This is going to be the first force that's acting on the object. In this case, for explanation, I'm saying that the object is a rock, but it can be any object that's falling vertically. So F1 is going to be the first force, and this is weight. Now, we have a formula for the weight of an object. If you remember, the weight of an object is given by its mass times the acceleration due to gravity. Okay. So if we want to write this mathematically as a mathematical formula, we would have m, which I'm going to make it clear later that the m is mass, and g, which I'm going to use to represent the force of gravity. Not the force, but just the acceleration due to gravity. And that's one thing to note. When you see the equation g equals 9.8 meters per second squared, it's very tempting to say that that's a force. But again, that's not a force. That's acceleration. You can see that it's acceleration because we're taking seconds squared, or a unit of time squared. Right? If you have a unit of time not squared, just a unit of time, that would be velocity. We have a unit of time squared on the bottom, that's acceleration. You have a unit of time cubed, that's jerk, etc. Okay. So F1 is the weight of the object, which we can write as mg, where m is mass, and we're going to use kilograms. And g is the acceleration due to gravity. Now, notice that I mentioned that we're in this one-dimensional plane, or not plane, this one-dimensional line where we can move along, and there's two possible directions, right? So for our purposes, we're going downward, but as I said before, you could also be moving upward in this line. Right? You have a line, there's two possible directions you can move. Just kind of like if you're doing a race, think of a 100-meter dash. You're either moving forward or you're moving backwards. Of course, you could kind of like move around in the lanes, but think that you stay in one lane. You either move forward or you either move backwards. There's two directions. It's the same with this situation here. Our rock is going down, but there's two possible directions. The rock could be going up if we actually threw it upwards. So what we're going to do is to differentiate between these two possible directions on this line, we're going to say that the downward motion is negative motion, so going downward, so we're going to add a negative in front, and upward motion is positive motion. Okay. So that means I'm going to add a negative here to make it clear that this is moving downward. Right? This is a force that's going downward. Okay. And let me make a note of that. Downward motion will be negative. Right? And then upward motion will be positive. This is something that we do to make the model less ambiguous, because again, there's two possible directions in which this force is acting on our object. It could either be pushing the rock down or the rock up. In this case, it's weight, right? So of course it's pushing the rock down. So we make sure to add this negative that I erased because it looked a little bit weird. Okay, so that's one force that's acting on the rock. You know, the force of its weight, right? Weight, acceleration due to gravity times its mass. It's pushing the rock downward. What other forces are acting on this object? Well, unless we're in a vacuum, another force that would be acting on this object is the resistance, air resistance. And I think you have experience with this, but basically, if you have a blank sheet of paper and then you put it horizontally and drop it, you'll see that it's going to move all over the place, and that's because there's air resistance pushing that paper upwards. Okay. Now, air resistance, like I said, is a force that's not pushing down, but it's actually pushing up. Right? So think of the resistance as telling you, okay, the rock wants to move down, air is kind of resisting that motion, trying to pushing it up. Of course, its weight is stronger than the air resistance, which is why the object actually falls. But there's still air resistance there, right? No matter what object you drop, as long as you're not in the vacuum, there's going to be resistance to that object. And again, that's a force that always goes, since your object is going down, that force is going to go opposite to the direction, which is in this case downward. So the force is actually pushing upward. Now, we want to be able to write this mathematically, kind of like we did with weight. And in fact, there's a way to do this. It's okay if you don't know. It's something I don't expect you to know. But in a lot of cases, specifically in a case like this, when we're modeling one-dimensional motion near sea level, we can actually assume that the air resistance is proportional to the velocity of the object. So actually, let me write it like this. Write it as a note. And again, you're not supposed to know this, but it's something that you can assume in a situation like this. So air resistance is proportional to the velocity of the object. Now, we usually write velocity. We're going to denote that with v, kind of like you did in Calc 1 and Calc 2. Use v for velocity. So if you want to write F2 as an equation, how do we do that? Well, we're going to write it like this. So what does it mean for two things to be proportional? That means that one thing is a scalar or a constant multiple of the other thing. So if I'm telling you that air resistance is proportional to velocity, that means that F2 equals a constant times the velocity. Okay. So now we have a mathematical equation for our force F1, which is the weight, which is going downward. That's why it's negative. And our force F2. Again, it's just air resistance, so it's pushing in the opposite direction of falling, so it's pushing upward. And for our purposes, that's positive motion. So we keep it as a positive force. And that's why I make sure that I keep K to be greater than 0. Okay. So now we have two forces acting on our object. Now, there could be other forces. Of course, the wind could be, in theory, forcing this object to move in different directions. For our purposes of this model, we're going to assume that these are the only two forces acting on the object, just the weight and the air resistance. Now, if you've taken physics before, let me use F sub net to denote the net force acting on the object. So the net force is basically just the sum of all forces acting on the object. So for our purposes, F net is going to be F1 plus F2. Those are the two forces that we're assuming are acting on our object. F1 was negative the mass times the acceleration due to gravity, and then F2 was some constant times the velocity. Now, why did I do all this work? The reason why I did all this work is because we're almost to a point where we can actually use this model. Why? Because, let me write this again. We know that F net equals negative mg plus kv. Not only that, but we know from Newton's, let's see, what is it? Newton's second law of motion, that the force or the net force acting on an object is equal to the mass of the object times its acceleration. So you remember that that law of physics, that force equals mass times acceleration? So what that tells us is that we have two ways of writing this net force. We can write it as this sum that we found before, and we can also write it as the mass of the object, which is falling, in this case a stone, times its acceleration. So we're going to use A for acceleration. Now, if you remember from calculus 1, there's a relationship between the velocity of an object and the acceleration of an object. Specifically, acceleration is the derivative of an object with respect to time, right? The change in velocity with respect to time. So what does that mean for us? We can replace this A with dv dt, leave the other side the same, and now what do we have? We have an equation that models the position of the object, and in fact, it's a differential equation because we have position here. Now, of course, if we look at this differential equation, what is a solution to this differential equation? Well, a solution is velocity, right? A function for velocity. So this is really, specifically, this is modeling the velocity at a particular time, but you'll see that you can easily get from velocity to position by just integrating. Because if we write S for position, if you remember, let me write it like this. If you write S for position, then V is the derivative of position with respect to time. So all these variables are related. So specifically speaking, this is a differential equation whose solutions tell you the velocity of the object at a time t. Then once we have that velocity, we can always get back to position. So this is our model. Now, we are going to simplify this a little bit when we actually try to find solutions. But notice the process that we did to get here. It's really a physics sort of process because we basically use Newton's laws of motion. And we also use calculus to be able to write these forces that are acting on the object in terms of equations that involve actual quantities and functions. So if you see, there was a little bit of work, but it really came down to two things. Find the net force acting on the object, right? The sum of all forces acting on the object. And then second, use Newton's second law of motion that tells you that force equals mass times acceleration, set both things equals to each other, and now you have an equation that models the velocity at a particular time. And again, that can also give us position just by integrating. So I'm going to stop here for this video. This is just an example of how you can use knowledge that you have from calculus and the knowledge that you have from physics or things that you can potentially look up to give you a model for something in the real world. A model of an object that's falling vertically close to sea level, where we assume that the only forces acting on it are its weight and the air resistance.